Welcome back. This is Dr. Christy Patton-Lokes. In Module D, Lesson 5, we're going to be talking about vapor pressure. To estimate vapor pressure, we use the Clapeyron equation. It's a theoretical relationship between vapor pressure and temperature. It says that the vapor pressure will change with temperature as the change in the heat of vaporization divided by that temperature and the difference in the volumes, the specific volumes of the gas in the liquid. So the heat of vaporization we will be talking about more soon, but for now what you need to know is it's how much heat is required to vaporize 1 mole of liquid at a particular temperature. In reality, heat of vaporization will be a function of temperature, but it does remain fairly constant through large portions of the temperature change until it starts approaching the critical temperature, and then it will change very drastically. Another thing to note is that gas volumes are going to be much larger than volumes of liquids. So we can simplify this equation somewhat by eliminating this very small term comparatively and treating this as a constant. So these are simplifications that we might choose to make. The clausius-clapeyron takes those two simplifications plus one additional assumption. So we're going to assume that the constant heat of vaporization is going to be correct. We're going to neglect the relatively small liquid-specific volume, and we will assume that the gas is an ideal gas, and these are specific volumes in each case. And if that's the case, then I can use the ideal gas law, so the specific volume of the gas, if it's an ideal gas, is RT over P. And if I do that, I'm able to integrate the Clapeyron equation. And we end up with this expression shown here. The natural log of the vapor pressure is negative delta H of vaporization divided by RT plus some constant of integration, which would be one known fixed value. Now, there are various ways that people have calculated these things, but one thing that an observant engineer might notice is that the graphs of P star versus 1 over T would be linear on a semi-log plot. Okay. A gentleman named E.R. Cox, he took that idea and graphed the vapor pressures for many, many common substances on this sort of graph. Now we're going to be looking at this on the next slide. I want you to pay close attention to the axes as we do this. These variables are not linearly distributed along the axes. In fact, if you look at the vapor pressure, which is along the y-axis, the traditional y-axis, it's going to be a logarithmic scale. So it's these ones like we had for compressibility factor where they count in decades, so 0.1, 0.2, 0.3, 0.4, all the way up to 1, and then instead of saying 1.1, we go to 2, 3, 4, all the way up. Okay. Across the bottom axis, we're going to have temperature. This is, remember it was the 1 over T. And so therefore the temperature scale is just kind of unique. And so you just have to read very carefully and approximate carefully. Now, most of the very common materials are shown on this axis here, or on this graph. And so let's say you wanted to look at maybe ethyl chloride. Ethyl chloride, it's going to start and stop. This would be, say, the triple point. This point here is going to be the critical point. Vapor pressure can only exist between those two values, and it will be a straight line. And if you knew the temperature, okay, if you wanted to know what the vapor pressure at, a nice cool winter day, I'll dream of that, 50 degrees Fahrenheit. I find the temperature, I go straight up, I read from the scale by going straight across. And so in this particular case, knowing this is a logarithmic scale, it looks like about 12 psi is the vapor pressure for ethyl chloride at roughly 50 degrees Fahrenheit. Now, most of the time we don't really prefer to use a graph to get an answer. Equations are going to be very much preferred. The Antoine equation is probably the best known of the equations that people use for vapor pressure. This drops the assumption that the ideal gas law is appropriate, that heat of vaporization is necessarily appropriate. What it does instead is it says, let's take that general form from the Clapeyron equation and fit it to actual data. So there are many, many choices of equations that one might use. The Antoine equation is the best known. It's been around, in constant use for the longest time. The way it is written in your textbook is log base 10 of the vapor pressure is a constant minus another constant over T plus C. So this correction T plus C, instead of just a straight T in the denominator, allows us to, first of all, use relative temperatures. So in the previous equations, I would have had to, because it came from the ideal gas law, I would have had to use absolute temperature. But this, by choosing C appropriately, I can work with units of T that are a little bit more convenient. So the way that it's set up in your textbook, temperatures in degrees C for their choices of constant C. The constants A and B will help this to give an answer where the vapor pressure is in millimeters of mercury. And that is a vapor pressure. These are an excerpt from the table in your book. So these are the Antoine equation constants using this log 10 of the vapor pressure form. And so we have many, many chemicals here. We'll have the chemical formula in case you weren't sure what the name was. And notice that it gives the constants, but it also gives a range where it's valid. And in particular, if you look at something like acetic acid. Acetic acid, we have one that goes from 0 to 36. We have another from 29.8 to 126.5. For the very low temperatures, you would use this set of equations. For higher temperatures, you would use this one. But there is a little range where they overlap. In general, it shouldn't matter much which one of these you use as long as you're appropriately in that range. However, if I had a problem and I was working it and I thought that I was probably going to also have the same substance at higher temperatures later, maybe I was going to take this material and I was going to run it through a heater, then I would probably want to use the one that would allow me to just use the same equation up for the higher temperatures. Similarly, if I had something and I was going to be cooling it later, I would probably wish to use the one that was for the lower temperatures. So you'll just have to kind of use your judgment in many cases. Next, let's look at an example. So we want to find the vapor pressure of water at 80 degrees C, which is the same as 176 degrees Fahrenheit. I know you could have done that conversion yourself, but I chose to do it for you to make life a little easier. We want to do this using the steam tables, which should be the correct answer. Okay, so this one should be what I would call correct. And we also want to use the Cox chart, which is probably going to be the least accurate, mostly because of our ability to read the graph, but it'll be a quick method. I just have to find the numbers on the graph and read it off. The Antoine equation, okay, now we have the Antoine equation and the clausius-clapeyron. The Antoine equation was fit to data. So this one will probably be pretty good because it was based on fitting the curve to actual data. Now there is a caveat there that's going to be pretty good as long as I am in the correct temperature range. Okay, and then we have the clausius-clapeyron, which is based on theory. Okay, so it's going to be theoretical with those three assumptions. It's pretty good if those assumptions are correct. Okay, so when would those assumptions be appropriate? When the gas is going to be more like an ideal gas. So when the overall temperature is high and the pressure is low, okay? And when the molecule is going to be small and spherical, okay? So those are going to be my ideal gas assumptions. And then I have the tricks of, is delta H vaporization constant? And I said that's going to be fairly good as long as I am far away from the critical point. So as the temperature goes up, the ideal gas law assumption gets better, but the delta H of vaporization assumption gets worse. So that's going to be, a little bit challenging to know whether or not that's good. So we'll look at now these answers. So if you go to the steam tables, and in the last print edition of the textbook, it was page 645. In the ebook, that doesn't even make sense. But if you go back to Appendix B, you can look. And what you're going to do is you're going to find the temperature. Now, the tables in this textbook are in degrees C, so we look for 80 degrees C. We find saturated steam, temperature of 80 degrees C, and of course, it's not really on the table. So what we have to do is we have to interpolate. Now, interpolation, you'll recall, says that I have a point where P star is 0.45 and T is 78.7, and I have another point where P star is 0.5 and T is 81.3, and I'm going to fit them with the correct line and say, well, P star equals what when the temperature is 80? So I can use differences, so rise over run, and if I think of this as P along this axis, okay, the point from here to here, P star minus 0.45 over 80 minus 78.7 should equal the slope going from this point to this point. So 0.5 minus 0.45 all over 81.3 minus 78.7. And the answer is very close to being 0.475 bars, which is, if you want it in millimeters of mercury, 356 millimeters of mercury. Now, to use the Cox chart, well, you find water, which unfortunately water is in the scrunchy portion of the graph, but there's water. You find that line, and I usually try to highlight it just so that I can find it more easily. I'm going to find my temperature. I want to use 176 degrees Fahrenheit. So find 176, draw a straight line up, draw across, and over here I will read my vapor pressure. And I found that to be about 7 psi, which is 364 millimeters of mercury. Okay, now based on your ability to read this very crowded graph, you're going to get very different answers. So you try it and see what you come up with. The Antoine equation, I just look up the constants in the book. Okay, it's in degrees C, so I'm going to use 80 degrees C. I found the constants. Those are in the book. I enter T as 80 in degrees C, and I solve for P star. Now recall that that means P star is going to be 10 to the power of all of that other mess. Okay, and so P star is 355 millimeters of mercury. And if we were to use the clausius-clapeyron, this is probably the hardest of these to use. I need to know what the heat of vaporization is, okay? If you look in the data table for water, at the boiling point, the normal boiling point, the temperature is 100, P star is 760 millimeters of mercury. That's because it is the normal boiling point. And the heat of vaporization at that point is 40.656 kilojoules per mole. For most chemicals, that would be the way that you would need to do it. So I'm choosing to use this. There is, of course, the option where you could have found the enthalpy of the vapor and the enthalpy of the liquid at 80 degrees C and subtract those, and that would have also given you the heat of vaporization for this material. Okay, this would be better. Okay, this one is the better, but you don't always have that as an option. So I'm choosing to show you the one that this one is going to be mostly available, okay? So we usually have this information. We usually don't have this information. If you have that, that would be a better answer. So we need to solve for what's the constant of integration. So I have my one fixed point. When the vapor pressure is 760 millimeters of mercury and the temperature is 100, with this as the heat of vaporization, then I end up with B is 19.743. Now you'll notice I use this as joules per mole, not kilojoules per mole, because of my choice of R. I want to make sure that the units cancel between my delta H of vaporization and my choice of R. So I ended up with 19.743. So now I'm going to plug that in and put in my actual temperature, 80 degrees here. Convert that to Kelvin, so add 273. I'm going to use the same heat of vaporization. I'm going to divide by 8.314, and I'll end up with 362 millimeters of mercury. So all of these gave answers that were fairly close, okay? Water has been well studied, so people sort of adapt a lot of the equations so that they are pretty good for water. Water's hard to model, but it's so prevalent that people do try to optimize that. Clausius-clapeyron was a lot of work, and it wasn't even the best answer, okay? Of these, I would recommend that we usually use data. So best choice is use data if you actually have it, okay? The second choice would be to use an Antoine equation or another one from data. Something that was derived from data. Third, if you're in a hurry, I would do a Cox chart. And at the very end would be when I would resort to using things like the clausius-clapeyron. They are when you have the least information, okay? That's when I use these. So this would be my personal preference for what order I would choose. I would first see if I have any data. If I do, I'm done. I don't need to do anything else. Next, I would say, well, maybe there's an Antoine equation set of constants. In case I do, use that. Don't go any further. And then next, I would go to the Cox charts or the clausius-clapeyron, and I would make that decision based on how precise I need an answer. So this concludes our discussion of vapor pressure. We're going to come back and see how this can be used in the next set of lessons.